Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, a division of HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Present the conference. Mathematical optimization models degenerate solutions. Cases in electricity markets. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. Mathematical concepts. Not all that glitters is gold. A solution is degenerate when there is more than one solution point for the optimization problem, such as at least two different decisions, which give the same result for the target function. A primal-degenerate solution with multiple optimal solutions implies that the dual solution is also degenerate, which implies basic dual variables, associated with active constraints, that are equal to zero, and that there are multiple solutions for the dual variables that optimize the dual objective function. Therefore, it is possible that both primal and dual problems have multiple degenerate optimal solutions. In a strictly complementary optimal solution, for each basic primal variable, the corresponding dual variable is strictly positive. Each non-degenerate linear program has a strictly complementary optimal solution. This implies that, if the slack variable of a constraint is equal to zero, the corresponding dual variable must be strictly positive. In what follows, the problem of degenerate solutions with multiple optimal primal solutions is analyzed, which in turn generate multiple optimal dual solutions, which implies sets of dual variables equal to zero for active constraints, that is, they do not comply with being strictly complementary optimal solutions. Optimization models can be degenerate. For ongoing issues, this means that primal, there are an infinite number of primal solutions that meet the conditions of optimality and viability of the problem. Dual, there are dual variables for active constraints whose value is equal to zero. The degeneracy problem is more common in linear problems than in nonlinear ones, and it is more frequent than users of optimization models think. The degeneration of the optimal solution is related to the multiple physical solutions, primal variables, that meet the economic conditions of optimality, dual feasibility, and those of physical feasibility, primal feasibility. In a convex, continuous, programming problem, these equa-optimal solutions, equal value for the objective function, are in a convex set, and the solution algorithms find only one point among the infinite number of points that make up the convex set. Several important mathematical and computational problems arise from degeneracy. Greater difficulty in solving optimization problems, therefore, greater demand for computational resources. In certain algorithms, degeneracy can produce cycles of degenerate solutions, in which the displacement condition in the gradient of the function must be positive, and not simply zero. In combinatorial problems, degeneracy can prevent the problem from being resolved. Difficulty comparing solutions obtained with different algorithms C, with the same algorithm under different parameterization, and minor changes in model parameters. Degenerate solutions can produce large visual differences in the operating profiles, maintaining in all cases the same value of the objective function. Several important mathematical and computational problems arise from degeneracy. Undefinition of the dual variables that are equal to zero for the constraints involved in degeneracy, and degeneration into a discrete problem can lead to not being able to demonstrate the optimality of the solution. In large-scale optimization processes, such as Bender's theory, degenerate solutions to a subproblem complicated solution, and variations must be implemented to solve these drawbacks, and the biggest problem arises in the degeneracy of slave problems, which if they have degenerate solutions will produce dual variables equal to zero and degenerate the cuts of the master problem. In 1979, Mignati and Wang created Pareto cuts to address the degeneracy of subproblems. Mathematically, a linear programming solution is defined as degenerate when there are primal variables in the basic solution that are equal to zero, which can cause a primal degenerate solution to involve multiple optimal solutions that are equivalent, because its reduced cost in the objective function is the same for all of them. Algorithmically, it implies that the simplex method can change a basic variable equal to zero to another basic variable equal to zero. This could involve an endless list of degenerate solutions. The following points should be considered with respect to primal, P, and dual, D, solutions. If a basic solution is equal to 0 for some basic variable, then we have a degenerate primal optimal solution. It is quite possible that we will then have multiple optimal dual solutions, but this is not necessarily the case. If D has multiple optimal solutions, then each optimal basic solution for P is degenerate. If D has a non-degenerate optimal solution, then P has a unique optimal solution. If P has multiple optimal solutions, then each optimal basic solution for D is degenerate. A feasible dual solution is degenerate if exactly more than m dual constraints are maintained. Equivalently, if dual constraints less than n-m are strictly maintained, where n is the number of variables. Bender's framework. Let's consider a linear optimization problem, whose feasibility zone is a closed polyhedron, with n extreme points, in this case 6. The contour lines of the objective function will instruct an algorithm to move out of the viability zone to optimize a convex problem. If the problem is not degenerate, the optimal solution will correspond to one of the extreme points of the polyhedron. If the resource vector is infinitesimally perturbed for any active constraint, it will automatically change the value of the solution by an amount defined by the dual variable of the constraint that has been perturbed. For non-active constraints, the corresponding dual variable will be equal to 0. If the isolines of the objective function are parallel to a hyperplane of the constraint polyhedron, in this case a line, there will be at least as many optimal ends as the extreme points of the polyhedron hyperplane. In general, all the points that are part of the convex set, defined by the hyperplane of the constraint polyhedron, will be a solution. If the resource vector is perturbed infinitesimally, in any active constraint other than the line with the objective function, the value of the solution will not change. This implies that there will be dual variables of active constraints, equal to 0. Hence the strict complementarity of the theory of duality, which says the variable slack multiplied by the dual variable will be equal to 0, and one of them will be different from 0, it will not be fulfilled. Another case of degeneracy occurs when the duality gap is not closed, such as when the solution produced by the algorithm does not reach the optimum, usually for convergence reasons. This usually occurs in discrete optimization problems, where closing the duality gap may be infinite. Degenerate solutions are found in convex set of equivalent suboptimal solutions. Another aspect that can influence the degeneration of a problem is related to the algorithms used to solve it. There are two alternatives. First, the outer point algorithms, such as simplex-type algorithms, which traverse the viability zone along the edge looking for optimality. In this case, the algorithm will tend to stop at the first extreme point that meets the optimal conditions, and for which it can be shown that there is no better solution. If the solution is degenerate, the algorithm may not be able to prove that it is in a solution to the problem and will follow the endpoint enumeration process until the last endpoint, when it will be able to prove that there is no better solution. This solution is basic, feasible and optimal. At the interior points, or penalty and barrier algorithms, the algorithm traverses the internal viability zone, quickly looking for the boundary where the solution is located, which will possibly be close to an extreme point, but often does not correspond to a feasible basic solution at an extreme point. If necessary, a crossover process should be performed to obtain a basic feasible solution at an extreme point. This will be the feasible basic optimal solution to the optimization problem reported by the algorithm. Feasible basic solutions are necessary to continue the optimization processes based on a dual simplex algorithm. The origins of degeneration may be of various types. For example, considering a network of water reservoirs, the dual variables will be equal to the gradient of the objective function with respect to the resources associated with the constraint. To establish the price of water at the beginning of an operating period, it must be equal to the maximum of the dual variables of the continuity constraints. This value must be equal to 0 if there is an abundance in the reservoirs, or equal to a positive value if the water resource is being depleted, and that the stored water is not enough to cover the demand for electricity, leaving the system dependent on water inputs and thermal generation capacity. Consider a simple case of a generational system composed of one central generation plant, with capacity of 300 megawatts, divided into three identical units of 100 megawatts each. The reservoir capacity is 1000 megawatts, the initial reservoir level is 150 megawatts and a contribution of 250 megawatts is expected. There is a second reservoir with generation capacity of 400 megawatts in one generation unit. The reservoir capacity is 500 megawatts, the initial reservoir level is 250 megawatts, and a contribution of 50 megawatts is expected. In addition, there is a thermal power plant with a generation capacity of 500 megawatts. One demand center, a city, which consumes a maximum of 1,100 megawatts at peak times. Let's consider how to meet demand at different times of the day, starting with peak demand. During this hour, the system is overloaded and must operate its generation units at maximum capacity. The solution to the optimization problem is normal, a one-size-fits-all solution. If the demand varies between 600 and 1100 MW, the conditions change. The optimal solution implies that hydroelectric capacity must generate at maximum capacity, and that surplus over 600 megawatts must be provided with thermal generation. The solution to the optimization problem is normal, a one-size-fits-all solution. If the demand is less than 600 megawatts, a situation will occur where no thermal capacity will be needed and there will be a surplus of hydro capacity. In the case of a demand equal to 300 megawatts, the solution to the problem is degenerate. One solution is to generate the 300 megawatts with water from Reservoir 1 and not use Reservoir 2. This is one solution of the multiple degenerate solutions. But there are more solutions, an infinite number, such as the one presented, in which generation is divided with the water from the two reservoirs. Another case of intermediate degenerate solution. In general, it is observed that excess supply generates degenerate solutions. Given the small size of this system, it is possible to determine the convex sets where the degenerate solutions are found. The equation that defines demand is equal to Z plus x1 plus x2 plus x3, where Z is the generation in the unit of reservoir 2, and Xi is the generation in each unit of reservoir 1. In this case, the degeneration does not affect the cost of electricity and, therefore, does not affect the city. The economic situation is different. If there is only one hydroelectric generator, the income of this generator, in a marginal market, will be indifferent to degeneration, it will always receive the same income. Therefore, it does not deal with the problem of degenerate solutions. Degeneracy and optimization of electricity systems. Common cases that produce degenerate solutions. Oversupply of resources with zero direct cost, examples. Unpaid capacity supply surplus substitutable water resources, in time and or space electrical power losses in different startup or stop times in scheduling problems multiple equivalent solutions in combinatorial problems. Resources whose costs are equal, which generates indifference between the use of resources. Imperfect mathematical formulations. In this case, degeneracy is introduced by the modeler, such as redundant systems of equations. Being aware of this type of problem, the mathematical modeler can introduce constraints and or variables to handle the problem, perhaps introducing a small distortion into it. Degeneracy is a problem associated with the input data of the problem, rather than with the formulation of the mathematical model. It is the solution that is degenerate, not the mathematical model. Degeneracy occurs in all kinds of optimization problems. Continuous and discrete, and linear and nonlinear. Degeneration is related to the water resources network, which occurs when there is an abundance of water. Degeneration occurs due to indifference in water use, whether in space, substitution of water between reservoirs, or, over time, substitution of water between periods. If it is only a matter of operating the reservoirs, there is no problem, but if the exploitation is linked to the remuneration for their use, This can generate economic problems in which a reservoir can systematically benefit. The image compares the results of two different runs. The image shows the SAW effect, which frequently occurs when the reservoir has no storage capacity, relative to the planning horizon periods. For the model, it is irrelevant whether the reservoir is full or empty. The two runs have the same effect. To obtain two different results with the same model, the reservoir codes were changed between the two runs. This is serious because if there is a remuneration for the operation, it depends on the coding system. The profile presents some points on which both models coincide. In degeneracy, it is totally indifferent to the model when these coincidences occur. The image corresponds to reservoir 2, which presents the SAW effect in one run, and not in another. If it were possible to standardize marginal costs in time and space, degeneracy would not produce differentiation in the rents generated, but this is not possible, and differential rents would be generated due to degeneration. Degeneracy can involve two agents using the same model to obtain systematically different solutions. In an electrical dispatch system, the problem of understanding and managing degeneracy can be complicated and even contradictory. At least two problems of degeneration are exposed. The problems of the water network are spread throughout the system. Losses in the transmission system can lead to multiple solutions when there is an excess of free resources. Electricity auctions. Typically, mathematical models seek to maximize an organization's economic benefits, without analyzing how the benefits obtained will be distributed. When there is only one actor affected by the benefits, it does not matter how the benefits generated by the mathematical model are distributed. But when the operations of the mathematical model affect the distribution of income, the situation can be complex. This may be the case of an economic group, or a cooperative, made up of multiple companies or agents, whose profits depend on operations. Degeneracy can produce multiple ways of remunerating stakeholders. Not all agents can be satisfied with the economic allocations, regardless of whether the operations maximize the benefits of the group or the cooperative. There are methodologies that can be applied to improve this situation, such as cooperative games. In many cases, the regulation of utility is supported by mathematical models that serve to analyze the impact of regulation, and determines remuneration based on its results. The degeneration of solutions entails problems associated with the remunerations assigned, which can also be degenerated. This leads to a problem of regulatory transparency, which produces economic outcomes that benefit some and harm others. In certain cases, these results could be manipulated by the agents involved in regulated gambling, based on a mathematical model that is supposed to guarantee transparency. This does not mean that mathematical models are not suitable to support the regulator, who must be aware of what the models imply to avoid undesirable situations. Below is a real case of regulating an electricity market to remunerate the support that a generating plant provides to the system. The regulation indicates that a mathematical model of economic dispatch is first executed, which produces a modified dispatch of plants, which considers extreme input parameters. From the modified dispatch of the plants, the algorithm BCR is executed, which produces the allocation of remuneration rights. To verify that the remuneration for backup capacity model produces degenerate solutions, the model was run 3 times, modifying the coding system used, SHT1, SHT2 and SHT3. Based on the numerical differences of the objective function, in practice, the 3 solutions are numerically equal, which implies degeneracy. Based on the results of the dispatch model, the BCR's remuneration must be calculated, which is also degenerate. In some cases, the magnitude of the difference in the generation assigned to some hydroelectric plants reaches 8%, a not insignificant amount. The table shows the degeneration in the allocation of the remuneration of hydroelectric power plants, which reaches a difference of 4%. These differences are converted into money distributed by the mathematical model, revenues that depend on the coding system chosen by market agents. This is not transparent. The starting point of the problem arises from the degeneration of the economic dispatch model. Graphically, it can be visualized how the degeneration of the dispatch model is transferred to the BCR algorithm. The problem is more serious, considering that degeneration may produce systematic results that always benefit an agent. It could happen that, for reasons of coding of hydroelectric plants, two plants compete by degeneration, one always generates and the other never. Trying to manage the situation, an agent could study how degeneration works, looking for the best conditions for it, in this case, select the best encoding system. It's a strange way to make money in an electricity market. Not all that glitters is gold. Alfred North Whitehead affirmed, "Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world." Thank you for your attention.